Hello and welcome to the lesson number 1 of Wave Optics Diffraction Physics KS 201. In this particular lesson we are going to cover the course outcome 1 to 1.4, which is relate physical optics with its application in optical devices. In the first lecture we are going to cover the basics of diffraction, the classification of diffraction, and the difference between the Fresnel and Fraunhofer class of diffraction. So basically, there are three different phenomena which can be explained on the basis of wave nature of light. The first one is interference, the second one is diffraction, and the last one is polarization. Diffraction is basically a property which is observed by treating light as a wave. And in this particular case of diffraction, we say that whenever the light passes through a particular slit or a particular object, then the light will deviate from its straight line path, which is against the concept of ray optics. So in diffraction we assume that whenever light falls on obstacles whose size is comparable with the wavelength of light, it bends round the corners of the obstacles and enters into the geometrical shadow, and this bending of light is called diffraction. So diffraction basically is observed in normal day-to-day life, in which if you place an object in between the slit and the screen or source and the screen, then you will observe that the image which is formed with the help of the object is slightly blurred, and this particular blurred image is obtained by observation of diffraction. Now this blurred image will have alternate maxima and minima if the sharpness of that particular edge of the object or the size of the slit is of the order of wavelength. So normally diffraction is bending of light, and this bending of light will result into different alternate maxima and minima, and in this case of diffraction there is a central maxima which is of the highest intensity, and on both sides of the central maxima there are secondary maxima of decreasing intensity, which is something different from interference. In interference you have all the maxima and minima of same intensity, all maxima of same intensity which are equally placed on both sides of the screen, whereas in diffraction you will have symmetry on both the sides, but the intensity will gradually decrease if you move from the center towards the side. Now the amount of bending depends upon the size of the obstacle and the wavelength of that particular wave. So in case of diffraction you need a slit or you need an object where the edges of that particular objects are sharp, and the slit width has a direct impact on the amount of diffraction which is observed. So if your slit width is very small, then you can easily observe a diffraction of smaller wavelength, but if your slit width is large, you can only observe the diffraction of waves having a larger wavelength. So diffraction is prominent when the value of the slit width and the wavelength of that particular wave which is used for the purpose of diffraction are of the same order. That's why the slit width which is used to diffract light cannot be used to diffract X-rays or gamma rays or ultraviolet rays, or the slit width which is used to diffract radio waves is not suitable for diffracting light. Now diffraction effects are observed only when a portion of wavefront is cut off by some obstacle, and in terms of wavefront we can say that Huygens theory proposes that light basically travels in the form of wavefronts, and it propagates in the form of secondary wavefronts, where the secondary wavefront is basically the locus of all the particles which are vibrating in the same phase. So as per the Huygens theory, whenever the wave travels, it has certain amount of particles which are vibrating in the same phase, and these particular particles will make sure that the energy is propagated in all possible directions with the same speed, and the outer envelope of all such secondary wavelets is basically termed as a secondary wavefront. So basis on the basis of Huygens theory of secondary wavefronts, we assume that whenever the light is trying to pass through a slit or is incident on an object, the particles which is at the edge of that particular slit or at the edge of that particular corner will create secondary wavelets, and these secondary wavelets will be passing into all possible directions, and they will now geometrically penetrate into the geometrical shadow of that particular object. So in this way the diffraction pattern is obtained, and this is all due to secondary wavefronts. So in this particular case of diffraction, we assume that it is observed whenever some part of the wavefront is cut with the help of an object or with the help of an slit. Now conditions for diffraction. The diffraction pattern is seen if the size of the diffracting obstacle is of the same order of the wavelength of light used. So if you want to observe a diffraction pattern of visible light, you need a slit where the slit width is of the order of wavelength of the visible region. Diffraction is more pronounced if the size of the obstacle is less than the wavelength of that particular light. So in this particular case of diffraction, it is observed practically that if the width of the slit is large, then the amount of bending will be less, and if we decrease the width of the slit, the bending will be high. So in case of a particular properly observed diffraction pattern, it is observed that diffraction will be more prominent when the width of the slit is of the order of wavelength. On the basis of the type of light used on this particular experiment, diffraction can be classified into two different categories. The first category is basically a Fresnel diffraction, and the next category is Fraunhofer diffraction. Now, in Fresnel diffraction, diffraction can be observed if the source of light and the screen at which diffraction pattern is formed are kept at finite distance from the diffracting obstacle, or in this situation the wavefronts falling on the obstacle are not plane wavefronts. Similarly, the wavefronts leaving the obstacle are also not plane wavefronts. So in case of a Fresnel diffraction, basically we can say that it is observed with the help of either a spherical wavefront or a cylindrical wavefront, and whenever a spherical wavefront or a cylindrical wavefront strikes a particular slit or an object, then secondary wavelets are generated which are again spherical or cylindrical in shape. So on the left hand side of the slit there is a spherical wavefront, on the right hand side of the slit there is also a spherical or a cylindrical wavefront. So no plane wavefronts are needed in this particular Fresnel diffraction, and there is a finite distance between the slit and the object, slit and the source, and then the slit and the screen. And if you change the distance between the slit and the source and the slit and the screen, the pattern will get modified. And the pattern which is obtained on the screen in the form of diffraction pattern is nothing. It is basically the modified image of the slit or the modified image of the object which is placed for the purpose of diffraction. So in Fresnel class we don't need any lenses because we are using the original light sources, and they are just producing the spherical wavefront or a cylindrical wavefront, and because there are spherical wavefronts and cylindrical wavefronts, then they are just imposed on that particular screen to get the desired wavefronts. So no lenses are required in case of a Fresnel class, and the distance between the slit and the source and the slit and the screen will be finite, and the type of wavefront which is used in this particular format is either a spherical wavefront or a cylindrical wavefront. And last, the object, the diffraction pattern which is obtained on the screen is basically the modified image of the slit or the modified image of the object which is used for the purpose of diffraction. So if I am considering a rectangular slit, I will observe a rectangular spot on the screen on which the light is coming, but the spot is slightly blurred due to diffraction. If I am taking a circular slit, I will see a circular spot on the screen with the circular circumference will be slightly blurred. And if I am taking a triangular slit, I will see a triangle shape of light with slightly blurred corners. So the image which is obtained on the screen is the image of the slit or the image of the object which is used for the purpose of diffraction, with a slight modified edges due to diffraction pattern. Now in case of Fraunhofer diffraction, we need a plane wavefront, and in Fraunhofer diffraction it is observed that if the source of light and the screen are at which diffraction pattern is formed are placed at infinite distance from the diffracting element, then there is no change in this particular pattern. This can be done by using two converging lenses, because there is a need of a plane wavefront in case of Fraunhofer diffraction. We have to convert this spherical wavefront into a plane wavefront, and then the plane wavefront is incident on that particular slit. So we need a lens which is basically of a converging nature in between the source and the slit, and the lens is placed in such a way that the source will be lying on the focus of the first lens. When the source lies on the focus of the first lens, it is observed that the light rays which are coming from that particular source will fall on that particular lens, and after refraction they will become parallel. That means we are converting a spherical wavefront into a plane wavefront. Now after passing through that particular slit, the plane wavefront will be slightly deviated due to diffraction in all possible directions, and in this particular figure we have considered two different directions, one going upwards and one going downwards, but the type of the wavefront will still remain plane, and we know that all the plane wavefronts will be basically formed with the help of parallel rays, and parallel rays will never intersect each other, so you are not being able to observe either a real image or a virtual image. So for the emission for the formation of diffraction pattern in the laboratory, we again use a converging lens, so that all the parallel rays which are diffracted will be now converged at some point on the screen to get the desired diffraction pattern. So there are minimum of two lenses required in case of Fraunhofer diffraction. The first lens is in between the source and the slit, and the second lens is in between the slit and the screen. And there is only one mandatory requirement, that the source must be placed exactly on the focus of the first lens, and the screen must be placed exactly on the focus of the second lens. And there is no essential requirement of the constant distance between the two lenses. You can have infinite distance between the two lenses, still the diffraction pattern will remain same. So in Fraunhofer diffraction, we use a plane wavefront. These plane wavefronts are obtained by placing two convex lenses. In this particular diffraction pattern, the distances are not mandatory. You can have any distance, but only the source must be placed exactly at the focus of the first lens, and the screen must be placed exactly at the focus of the other lens. Now, in this way, we can say that the diffraction pattern which is obtained on the screen is nothing. It is basically the object image of that particular source, which is found with the help of two different lenses. So in case of this Fraunhofer diffraction, the diffraction pattern obtained on the screen is the image of the source modified with the help of the diffracting element, whereas in Fraunhofer Fresnel diffraction, it is the image of the slit or the image of the object. So if I compare both these Fresnel class and Fraunhofer class of diffraction, I can easily say that in case of Fresnel diffraction, if the source of light and the screen are at finite distance from the obstacle, then the diffraction is called Fresnel diffraction. And if the source of light and the screen are at finite distances from obstacle, then the diffraction is called Fraunhofer diffraction. The corresponding rays are not parallel in case of Fresnel diffraction, and the corresponding rays are parallel. There is some typing mistake. The corresponding rays are parallel in case of Fraunhofer diffraction. Now, in Fresnel diffraction, the wavefront falling on the obstacle are not plane wavefront, because they are cylindrical wavefronts or spherical wavefronts, whereas in Fraunhofer diffraction, the wavefront which is falling on this particular slit is basically a plane wavefront. And to convert spherical wavefront into plane wavefront, we need we need a converging lens in the laboratory, and by that way we can easily convert a spherical wavefront into a spherical wavefront. So this is all for today's class. Today we have discussed about diffraction, which is basically a phenomena which can only be explained on the basis of wave nature of light, and it basically represents the bending of light from an object or of a particular slit, where diffraction has only one essential requirement, that the width of the slit must be of the order of wavelength. Now in the next lecture, which is scheduled tomorrow, we will cover the diffraction due to single slit, that too based on Fraunhofer diffraction, and the width of the central line.